Frost circles Canada. Why draw a circle anywhere else?
Hi there, my name is Eric, and for the fifth and final time, I will be teaming up with James and Brendan, and we will be talking about frost circles. In particular, we'll be talking about that of benzene, borazine, not quite sure how to pronounce that one, as well as cyclopropanol. So, without further ado, as always, let's get into it, and let's do it.
I'll be looking at two different triangular examples for the frost circle diagram method. So the first one that I'm going to be looking at is the cyclopropanol anion, which has 4 valence electrons, 1, 2, 3, and 4. And the second example that I'll be looking at is the cyclopropanol radical with 3 valence electrons, as you can see, 1, 2, and 3. So for the cyclopropanol anion, the first step, and this is the first step for any frost circle in general, you want to label your energy axis with E, and then draw a circle in the middle of it. So the second step is just drawing in the triangle, and make sure that the lowest point of the circle has a vertex touching it. This is going to be the bonding molecular orbital for the cyclopropanol anion pi system. And then these top two here are going to be your anti-bonding molecular orbitals. So the third step that you want to do is, I just drew out the little molecular orbitals here to make it easier. And then this line through the center of the circle represents non-bonding. So if there was an electron on this line here, it would be non-bonding, and anything below it is bonding. Anything above it is anti-bonding. So next, and the final thing we want to do is just fill in these 4 electrons into our pi system. So 1, 2, 3, and 4. And that's really all you need to do. And before I move on to the next one, it's important to note that this is an anti-aromatic compound because it is very unstable. So the next one that we're looking at is the cyclopropanol radical, and this is going to be very quick because it's basically the same as the anion, except for the fact that it has 3 electrons in the pi system instead of 4. So it does have a key difference though, which is the fact that it is not aromatic, but I'll explain that after I fill in the electrons, which is just 1, 2, and 3, and that's really all there is to it. And this is non-aromatic because it has 3 electrons, which is an odd number. If it had an even number, it could either be aromatic or anti-aromatic, but since there is only 3, it is out of the question. It's not aromatic.
So, benzene, or C6H6, has the MO energy orbital of a frost circle. It contains 6 carbons and 6 hydrogens, where each carbon atom contributes 1 pi Z orbital to the pi system. One key indicator that we know it's a frost circle is its resonance structure here. You can see it's got double bond here, 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 and here. However, this could also be flipped to where the single bonds are. That's how we know it's a resonance structure. Regarding benzene, we mix 6 atomic orbitals and we get 6 molecular orbitals. A crucial piece of information that we also know is that since all of the carbon atoms have 3 sigma bonds and 1 pi bond, resulting in 1 electron in the pi system per carbon atom, means that we will have 6 electrons total. So when we put the electrons in from bottom to top, 1, 2, 3, 4, 5, 6, we can see that we have our HOMO, or our highest occupied molecular orbital, here on the alpha plus B, and we have our LUMO, the lowest unoccupied molecular orbital, here at alpha minus B. And these are benzene's frontier orbitals actually. So the frontier orbitals are at alpha plus B with the HOMO and alpha minus B with the LUMO. Now on to Eric explaining how benzene MO would change for borazine.
So now that we know all about benzene and its frost circle, we can explore how the molecular orbital diagram can change for borazine. Borazine and benzene are fairly similar in the sense that they both have 6 sides to them with branching hydrogen atoms. However, if we take a look at this quick sketch I just drew of both of them, it's pretty quick. It's pretty easy to spot that benzene here, that we already know is made up of 6 carbon atoms, whereas borazine up here is made of alternating boron-nitrogen molecules instead of the carbon. So what does this mean exactly for the molecular orbital diagram? Lucky for us, they're actually fairly similar, especially because there's the same number of electrons used in the pi bonding and anti-bonding for both borazine and benzene. However, since there are boron and nitrogen atoms used in place of the carbon atoms, there is a greater energy difference on the molecular orbital diagram, since nitrogen has a greater electronegativity than carbon and boron has less of an electronegativity than carbon. We can illustrate this by looking at the molecular orbital diagram of borazine, which I have right here, a rough sketch at least. And as you can see, there are a lot of similarities with benzene, such as the alpha is dead center, as for, well, all molecular orbitals diagrams. And then the very bottom would be alpha plus 2 beta, and the top would be alpha minus 2 beta. I know that's a little difficult to see there. But that is similar across all molecular orbital diagrams. You'll notice here that I have labeled the highest occupied molecular orbital as alpha plus beta, and the lowest unoccupied molecular orbital as alpha minus beta, similar to that of benzene. Although this is just a rough sketch, you may also notice that the energy difference between the lowest molecular orbital and the highest molecular orbital, it is a greater energy difference there than there is with benzene. Again, that is due to the boron and nitrogen atom having a greater difference up there and over there. And lastly, I just like to point out here, as I previously stated, there's the same number of electrons in the pi bonding and anti-bonding molecular orbital, which we're looking at here, for borazine in comparison to benzene. They both have 6 electrons, which we can see here. There's 2, and then there are 4 at these in this set of double degenerate molecular orbitals. Lastly, I just forgot to mention here that the HOMO and LUMO that I have labeled here and here, those are the 2 sets that exhibit double degeneracy across the 2 of them respectively. And so that there is another similarity with benzene, with the double degeneracy there.
Thank you for tuning in to our presentation on frost circles, including benzene turning into borazine and the changes there. On behalf of Eric, Brendan, and I'd like to thank you guys for being our TAs.